Good, thank you. So thank you very much for being here. So this is a modified version of a talk, a keynote I gave at the first Open Networking Summit. And it's been modified to talk a little bit about the last couple of years. So the goal is to try and tease out some of the major trends and to clarify some of the major concepts behind SDN. There's a lot of excitement and energy and enthusiasm and articles about SDN, but they don't always say the same things. And I think often we're very confused by even what SDN means. So what I would like to do is talk a little bit about the history, clarify some of the misconceptions, and then talk about what about the community is so exciting. Before I do that, I want to be very clear that SDN and OpenFlow and network virtualization and all of these technologies have been created by thousands of people, and I am only a spokesperson. And so I don't want to diminish the value that so many people have put into this. So let me start with some of the original motivations. I am a failed physicist. So I did my undergrad largely in physics, but it was actually too hard for me. And so I moved to doing computational physics, which is using computers to solve physics problems. And my first job was working in a national laboratory doing computational modeling. So modeling physics phenomenon on supercomputers. After 9/11, I was moved from computational modeling to the intelligence agencies, where I worked on some of the most secure networks in my experience ever. And it was there that I started to realize that networks have very different properties than computers, where in order to implement very sophisticated security on computers, we could program them, but with networks, we couldn't. So I want to talk a little bit about what some of the problems were. So here is a network, it's an example, that we were trying to secure. And so in order to do that, we would have to put policies at different points to make sure that packets would hit all the policy. We'd have to structure the topology in a very specific way, otherwise we couldn't script it. We had to treat different switches differently. So for example, we had different policy in the top of rack than we did later on. And there was a lot of configuration throughout the network. So at the time, I wasn't a big networking guy. But I had taken networking classes. And I'd always learned that networks could handle failure, were easy to scale, were easy to manage. And in reality, the networks I was dealing with were very, very different. Right? And so there was this theoretical view of a network, and there was this reality, which there was almost no redundancy, so a failure could limit availability. The topologies had to be very rigid, so you couldn't grow this organically. If something changed, it would take days to fix it. Right? So networking, if something changes, I always thought it would heal immediately. But here, it would take humans days to reconfigure the topology. And it was impossible to build large networks because they were too difficult to manage. So if you look at this, you can ask yourself, what is the problem? Is it that we're bad at managing networks? Or is there a problem with the architecture? So I'd like to argue that this is actually an architectural problem. It's not that we had bad software or bad operators. It was actually architectural. So let me describe that very quickly. If you look at a switch data path, you've got tables, and these tables have forwarding state. Some of this forwarding state is populated by algorithms and protocols. And if that's the only state you have, networks would be great. If a link failed, they would converge. They would scale to the size of the internet, which they do. And there would be nothing humans needed to do to manage them. However, if you look at a switch, there's more than just forwarding state. So every packet will touch the blue state, which is dynamic state, but there's also other state that is programmed manually, things like tagging rules, or ACLs, or QoS configuration. And unfortunately, this is the type of state that we use to implement interesting things in networking. And unfortunately, these are managed by humans, not by algorithms. And so since every packet touches both state, the network reduces to human management of state. So here's what I would characterize the problem with the architecture. Humans are terrible at state management. We're slow. We're forgetful. We're error prone. If you compare this with traditional networking, if a link fails in traditional networking, the network converges in 50 milliseconds. For a manual state, the link changes, my beeper goes off, I wake up, I go to my phone, I drive to work. This is the difference of milliseconds and hours. However, even if we had programs instead of humans, at the time, there was no way to actually program a switch. There was no interface. It didn't exist. I mean, I worked for the government. We had a huge expense account, a huge budget, and we couldn't buy programmable switches. And even if you did have that, as a discipline, we don't know how to program in a fully distributed way, which is what is required by networking. So my background is distributed programming, and it's really hard. But for all network functionality, you must do full distribution. So I left the intelligence agencies, and I went to Stanford, and I worked with many people at Stanford to develop a lot of these initial concepts. And if you think about what is the motivating problem statement, the simplest way you can describe it, it's as follows. The question we are trying to answer is, if I want to do something new, how do I program a network? That was it. That was the problem statement. Which technically really is, how do I manage all of the forwarding state in a network programmatically? That's the technical definition of this problem. That's all the work we were looking at. So we identified two problems in the architecture, which we fixed. The first one was there's no interface to manage that state. And most of the forwarding functions were fixed in hardware. So there's no way for me to describe in software what I wanted to do and have the hardware implemented. Instead, what I would have to do is I would have to build more hardware, which would take 4 years and a lot of money. So the first thing that we fixed was we said, instead of having fixed hardware, I'm going to generalize the hardware so that you can describe what you want to do in software and then implement that in hardware. And that became OpenFlow. So that was the first problem we solved, generalizing the hardware. The second problem was that's actually not enough, just having programmable hardware. Because if I am writing programs, I need to make sure that I can write any type of program I want. And traditional networking required me to build a distributed program, which, as I mentioned before, is very difficult. So he said, instead of requiring distributed programming, which makes things like strong consistency impossible, or distributed consensus impossible, let's allow the programmer to use any distribution model they like. The programmer can do centralized. The programmer can do limited distribution. Or the programmer can do full distribution. But let's decouple those two. And the result was a very simple architecture, but a change in the architecture, which is here, you've got a generalized hardware abstraction layer. And here is where you implement the functionality. So the first system that we implemented was called Ethane. And it was basically a compiler for the entire network. Now, the goal was I want to declare security policy in a high language, and I want to build a compiler that will manage all of the forwarding state. And so if you look at how Ethane worked, is you would write, here's all of my security policy rules. It would go into the controller. This would compile it, and the forwarding rules will all set correctly. And here's actually a picture of this. This is when I was much younger in 2006. And this was the first Ethane system. So I think this is the controller here. And these were switches. So that was the system for which many of these things were based. From there, it was very easy to generalize the concept. Ethane was a fixed function. It only was a compiler. So why not generalize the idea so you can write many applications? Not just a compiler, but maybe visibility or billing or mobility. And that's where the network operating system came. So the network operating system is one more layer, which is decoupling the applications from the infrastructure. And that is what in 2009, based on an article in the MIT Technology Review, became SDN, or became titled SDN. So the ideas were very simple. To start off with, how do you program a network? Fix two architectural problems. One, make the forwarding generalized in hardware so you can control it programmatically. Two, change the distribution model so I don't have to write distributed programs. And then generalize the concept. That's what became SDN originally. So even though that I've described this to you, there's still a lot of confusion about what this is. I think the press writes articles that confuse it. I think marketing departments in companies confuse it. So I'd like to go through some of the basic misconceptions and answer or try and clarify these things. So the first one is, what is the value of SDN? Often I'll hear people say, it makes network operations simpler, which is not true. It's a mechanism. It's not a product. So what is the primary value proposition of SDN? First, I'd say it's the ability to innovate within the network. If you want to build a new network system, SDN is a good way to do it. Not only that, if your new network system requires more sophisticated control functions, for example, it requires strong consistency, or it requires complex algorithms that can't be distributed, it's a good way to do that. I don't think you can build a distributed compiler without having some centralization. I don't think you could have done ethane in the traditional architecture. But there's also a market benefit. And in the last 50 years in computer science, every time we decouple software from hardware, the markets become very efficient. You get competition at every layer. You get faster innovation speeds. And so I think all of these are benefits of SDN. So there's always the question, and this happened a lot more earlier than now, where, for example, I would be giving an interview, and the reporter would say, well, does SDN offer new functionality, like new security or something like that? I don't think it does, right? It's a way to build new functionality. It's a way to build new security. But itself, it's just an approach. There's also a lot of early concerns on things like scale. It was funny, I was actually going through my early notes on when I gave this talk 2 years ago. And at that time, we just tested an SDN system with 5,000 end hosts. So now, 2 years later, I can tell you, we've tested a system with 100,000 end hosts. And so early on, there were concerns with scalability when you change the architecture. Now, many years later, we have many production examples of SDN systems that have been used at scale in production in some of the most demanding environments in the world. So quite simply, yes. This is one of my favorites. There's also a claim that SDN makes it easy to program networks. So I actually don't believe this is true. So I've worked on 4 controllers, 4 SDN controllers, 3 SDN products. And I would like to describe why it doesn't make programming easier. On the left, you've got the traditional architecture. In the traditional programming model, you have switches and routers which will create a topology of the network, and they have control logic that works on that topology. In SDN, you have the exact same thing. You have controllers which create a topology, and they have logic that works on those topologies. In both cases, your control logic has to manage each switch, each link, and you have to handle communication between the controllers. So while SDN does allow you to write more powerful programs and more powerful control logic, it's still hard. So building a basic controller is not a huge effort. Building a functional product takes a lot of time and a lot of people. And I think acknowledging this is important because we want to focus on the value of SDN, which is I can now build systems with stronger properties, but it doesn't make it easier to build that system. So this is a timely topic. There's a lot of confusion between SDN and network virtualization. So often people don't know the difference, for example. So let me try and clarify that from my perspective. So what is the difference between SDN and network virtualization? SDN is a mechanism. It's an approach. It's a way to build something. But by itself, it doesn't solve any direct, say, customer problems. I like to think about it as a way to build an engine. It's not an engine, and it's not a car. It's just a way to build it. Network virtualization, the whole goal is to solve customer-facing problems. So instead of operators dealing with the physical topology, which changes and is complex, operators, customers, deal with a virtual abstraction of a network. So SDN is a mechanism, network virtualization, a solution. I think there's so much confusion on this, I wanted to draw a picture. So I was talking with actually one of the most famous analysts recently. And the analyst said, if you have SDN, you've moved the network into software, therefore it's virtualized. However, the reality is even with SDN, you still have to, the control function has to deal with every switch and every link. What network virtualization does is it has a layer which exposes a decoupled topology. So now operators or control logic operates on a simpler view of the network. So SDN is a great way to implement network virtualization. It's a great approach, but it is not network virtualization. Similarly, network virtualization does not have to be implemented with SDN, though I would argue it probably should be. Okay, so in the last bit of the talk, I would like to step back and, given everything that I've said, focus on what part of SDN and OpenFlow in the last 7 years I believe has the most value, right? Because I think us as a community, we want to think clearly, and we want to focus our efforts in the right way to continue to have the success that OpenFlow and SDN have. And so if we step back and we reflect, what really is the value of SDN? I say OpenFlow here. Are these all new ideas? Arguably not. Arguably, these ideas have been around for quite some time, right? Centralization isn't new. Programmable forwarding isn't new. Are the technologies this is based on well designed? Some are, some aren't. I don't think that they're particularly special. Is this a path to new functionality? Maybe, probably. I think that there's some value there. But I don't think that this provides us with the level of excitement and energy that we've seen. And so I like to ask the question, why is SDN and OpenFlow something I've dedicated, the last 10 years of my life to, and something I'm still very excited about, and something that I still focus on every day? Right? And why has it been so successful? I mean, why is there an SDN workshop in Japan and all over the world and in every publication? And I believe fundamentally the most exciting aspect of SDN is actually the community that's around it. And I want to be very serious about this, which is technology and research without community and without energy and without excitement is a waste of time. It's pointless. And it's not enough to create new technologies, and it's not enough to create slide decks and marketing literature. What we need to do is get together and work together and evolve technology. And SDN, in my experience, is one of the few times in the history of networking where we've had this level of energy and this level of involvement. And it's not just conferences. It's affected vendors. It's affected users. There are new products based on it. There are whole divisions based on it. And so I'm very happy to see that SDN workshops are happening in Japan, and I'm very happy to see that everybody is here. And so I just wanted to end my talk by thanking all of you for coming and saying I'm very excited to continue working with you as we go forward. Thank you very much.